Hi there, in this video we're going to be talking about length contraction, and this is an issue that arises as a result of objects travelling at relativistic speeds. Now let's take the situation that we've got here. We've got the Earth and our nearest star, Alpha Centauri, and we would like to send a spaceship from the Earth to Alpha Centauri, and a person standing on the Earth, there we go, measures the distance to Alpha Centauri at 4.4 light years. Okay, that's how far away it is. And we've just invented a spaceship, and this spaceship can travel at a speed of 0.9 c, 0.9 times the speed of light. So we've been working pretty hard there, and we've got a new spaceship. So how long is this spaceship going to take to get from the Earth to our nearest star, Alpha Centauri? Well, we do a very basic calculation. We use speed equals distance over time, and we bring time up and bring speed down. So that means the time taken is going to be the distance, which is 4.4 light years, divided by the speed, which is 0.9 c, and that works out to be 4.9 years. Okay. So the person standing on the Earth would see the spaceship leave the Earth, travel across space, and reach Alpha Centauri 4.9 years after it left. Okay. Now, thinking back to the previous page, the previous topic about time dilation, when you travel at relativistic speeds, the amount of time you experience reduces. So someone standing still will experience more time than you have. If you're on this spaceship travelling at 0.9 times the speed of light, it won't appear to have taken 4.9 years for you to have travelled that distance. So let's work out how long it will have taken you. And so the formula we use is delta t is equal to delta t naught times gamma, where, remember, gamma is 1 over the square root of 1 minus v squared over c squared. And in this case, delta t and delta t naught, let's define what they mean. Delta t naught is, the easiest way to remember it is it's the shortest time, and this is the longest time. So who experiences which time is the question you have to ask. Well, if we remember that time is shorter for the person travelling fastest, delta t naught is the proper time, so it's the time experienced by the traveller. And delta t is the longest time, so that's the time experienced by someone who is standing still, who's not moving at all, relative to the thing that the object's moving through. So the person on the Earth is the stationary person and experiences delta t. So let's work out then how long the time is. We know that the longest possible time is 4.9 years, so that equals delta t naught times gamma. So we need to work out what gamma is. That's 1 over the square root of 1 minus v squared over c squared, which is the same as saying 0.9 squared, and that works out to be type that in, 2.294 not years, 2.294. That's what gamma is equal to. And so we can then put this into this equation here to get 4.9 divided by gamma, 2.294, and that equals 2.136 years. Okay, so the person on the spaceship only experiences, between leaving the Earth and arriving at Alpha Centauri, 2.136 years, which is considerably less than the 4.9 years experienced by the person who's stationary on Earth, or indeed they could be stationary next to Alpha Centauri. It's a star, so they couldn't be be on it. Let's have a little think then about what that means about the distance the spaceship has travelled. If we use the old formula, speed is distance over time, they both agree on the speed. They both think that the speed is 0.9. Okay. The person standing on the Earth thinks the distance travelled is 4.4 light years, and they think they do that in 4.9 years. So that's their equation completed there for the person on the Earth. For the person doing the travelling, they agree that the speed is 0.9 times the speed of light. They've got a speed dial on their spaceship. They're in control of the spaceship. They know how fast it's going. So what do they think about the distance? Well, let's leave that one for now. They know the time. We just worked that out. That's 2.136 years. Now, the only other variable in this equation is d, and it can't possibly be 4.4 light years, because if it was, one of these numbers will be different. So when objects travel at relativistic speeds, the amount of time they experience reduces. It's less than a person who's stationary, and the distance they experience as well also changes, and we get the equation L equals L0 divided by gamma, or we could rewrite that as L equals L0 times the square root of 1 minus v squared over c squared.